We are recording now. So today I'm going to go over the quiz because on Wednesday we will have another quiz like that one. And I want to go over Insight in Revit because we have free access to Insight. We're not using this for the final exam, and well, I'm still thinking if we are going to use this for the final report, because things are getting complicated with Revit and Insight and Grid Building Studio. And I don't know, let's analyze the results, and then we will see if you can do something with the Revit Insight. But first, I want to go over this quiz. Okay, so for this quiz, we have the building, the PV array, and this is the most important thing on the quiz, because if you have this, if you can't enter the DC size on PV watts, then everything else is wrong. Okay, so, and it's quite easy. So the thing is that on PV watts, after introducing the location in New Hampshire, we have to include the DC system size. We have data, the tilt is 15. Tilt is 15. Then we have the azimuth. If it's south, it will be 180 by default. We don't change the, well, we are going to use always the standard module, the fixed open rack, and the same system losses. So we're not going to change any of this, but we have to change the DC system size. Okay, so this is the most important thing, because if this is wrong, then everything else will be wrong. And it's quite simple. We have, for the DC system size, we need to type here a number in kilowatts. So if the, and here we have different data. We have the maximum power of the panel at the standard test conditions. And then we have the power per area. So this power per area is the maximum power at STC divided by the area of one panel. And then we have the total area of the PV array. So if we want to have the total power, we have to multiply the power divided by area times the area of the PV array. Okay, so in this case is 150 watts per square meter times 1,000 square meters. So the DC power will be 150,000 watts. Since here we have to introduce kilowatts, then we have to type 150 kilowatts. Okay, so this is the first thing. If this is wrong, then everything is wrong. The tilt, well, the tilt, you only have to read it, and if you can read the angle of the tilt. But for the DC size, you have to do this. So I will give you data about the panel and about the area that we have in our building, and then you have to calculate the DC system size. Okay, once we have this, we can go to the results. Okay, and now we have to start copying these results here. So I'll go to the preview. Yeah. What is the yearly production of the proposed PV array? So the yearly, it's both work. So this is rounded down and this is rounded up. So both answers would be correct. So let's copy this one. Okay. Second, what is the monthly production in January? So in January, we always have to look at this column, the AC energy. So in January is 10,727. And what is the monthly production in July? In July is this one. Okay. Then this is the challenge of this, because these answers, the first three answers are pretty straightforward. We only have to if we have included the right DC size and the right tilt, we only have to copy first this value and then any of the monthly values that we have here. But here we have to download the hourly data from PV Watts and include all these for January the 1st and for July the 1st. So remember that we can download the hourly. So here we have an Excel file. We open that Excel file. Okay. And here we have all these. As you can see on that quiz, in January the 1st, we have 8 hours. Well, maybe this is confusing. I will make it clearer next time. But as you can see, here you have to include numbers that are not 0. Okay, so if we are working with this, here we have 1, 2, 3, 4, 5, 6, 7, 8. So you have to go to this column, the AC system output in watts, and then you have to type this number. Without decimals, it's fine. Okay, so that would be the first hour. That would be the second. Third. And 8. Okay. So some of you have started with 0. Hour 1, 0, 0. No, I will make myself clear next time. But you have to start typing or here the first hour in which we have production. Okay, so there is no point of having 0, 0, 0, 0. So you have to include this. And then for July the 1st, we have to go to July 1st. Okay, on July 1st, we have more hours. We have up to 15 hours in which the array is producing energy. So we have to type these values 15 times. 1, 2, 3, 5. 15. Okay, that's it. You have to copy without any decimals. And you have to paste this value here. And then finally, we have to produce the graphics. So I'll do it again. On January the 1st, we need this input. Okay, so we have to go to the 23rd hour. And then we have to create, insert one of these charts like this. And then we have to copy this one. We have to go to July well, no need to copy. We're going to go to July the 1st. Here, we can insert one of these charts. Well, if you select the values first, from 1 to 23, and then insert this chart, you get this. Okay, now you have to copy this into a PowerPoint and the other one into the same PowerPoint and upload the file there. We submit the quiz. You have and it's correct. Okay, I didn't upload it. And why is this question incorrect? You can see they're the same. Well, I don't know. This shouldn't be incorrect. Anyway, I'll check this because the rest of the answers are correct. But maybe I made a mistake when I was copying and pasting these options. Or this is a comma. Yeah. Oh, I'll check it.
Yes, it's correct. The answers are hidden, so I don't know.
Yeah, they're correct answers. Yeah. So I don't know why this is incorrect. Because it's 10,000. Maybe I copied a space or.
Yeah, I don't know.
Okay, so I'll check this and I'll make sure that even if you copy a space before or after the number, the answer is correct. Okay, so this is the quiz. And I'll prepare another one. But it's always the same. We have to calculate first the DC system size of the PV array. Then we have to look at the monthly and yearly results. And finally, we have to download the hourly results. And then we have to work with specific days or specific hours. Another question can be, okay, if we are in July the 8th at noon, what is the production? So you have to go to July the 8th at noon. It will be hour 12 here, and this is the production that we are looking for. Okay, so you have to get used to working with this file and to find the right answer. It can be yeah, any day at any time, you have access to this, and then you have to copy and paste this data on the quiz. And you have to get used to working with these graphics, because they are very useful, because at a glance we can see what we are doing. And it's even better if we prepare like a monthly. I think we did this on Wednesday. If we want to see the performance in January, we can always insert another graphic like this. And this is the performance in January. And if we want to see the performance in February, you can select all this data in February. And then insert. Okay. So now, if we have the same scale, and this is important, we can see that the peak production in February is higher than the peak production in January. So the peak is around 100,000. And in February, we have 3-4 days in which the production is above 100,000. If it's cloudy in February, we have the same production as a cloudy day in January, okay? But as we are moving on, the PV production, the peak PV production has to be, let's do it monthly, because I think it might be interesting. And I'm going to copy this on a PowerPoint. Okay, this is January. Then this is February. It would be great if you can change the chart title to January, February. Now we have to select March. So it's month number 3. We start here, go all the way down until the end of March. We can insert and we have this chart title, which is March. The next one is April. Okay, so by looking at this, you can see how now the scale has changed because we are moving beyond 120. Okay, so at the end, we should adjust all the scales. And if the peak production is like this, I don't think it will be, let's do June and July, May and June. Sorry. Insert May. June. Okay, look at this. That's interesting because in June, we have less production. So the peak production in June is not 140 or above 120. Because why is that happening? Probably because of the temperature of the cell. Okay, because in June or July we're going to have more hours, more sun hours than in May or in April. But if the cell heats up, it produces less energy. Okay, so that's interesting. And it's not that, okay, we have good weather, hot summer, so we will produce more energy in summer than in winter. It's not always like this. So this technology is complicated because the amount of sun, the hours of sun, of course, matter, but the temperature of the cell matters as well. So in summer, we will have higher cell temperatures, and that will reduce the energy production. Okay. So anyway, I think it would be interesting if we were adjusting the scale. Okay, so we can do that, and we can go to axis option. And if we adjust the scale of all these graphics to 140, that's better because when we are comparing March or April and this is June, we see that the peak production in April is higher than the peak production in June. Why? Well, because in April we have a lot of hours, sun hours as well, and the temperature is not as high as in June. So for the PV performance, it's better in April than in June. Although the total, because that's the other thing we have to analyze, the total performance in June, you see that it's higher than the total performance in April. This is because we have more sun hours in June than in April. But the peak performance is higher in April than in June. Okay, so this is the kind of things that we have to analyze. It's about the total production, the peak production. So those are values that we have to analyze and try to understand what's going on. Because if you don't know anything about PV panels, you would say, okay, in January, we're going to have a very low production. And it makes sense because we have, look at this, look at the high amount of cloudy days that we have in January. In June, we have a couple of cloudy days, but most of the days are clear. And even in April, we have more cloudy days, but when there's sun, the peak production in April is higher than the peak production in June. So that has to do with the cell temperature. Okay, so these are all the things that we have to analyze. The total yearly production, and with the total yearly production, we can analyze different orientations, or we can analyze different tilt angles. Okay, so what is the maximum or the best tilt angle in terms of the yearly energy production? So that makes us make the first decision of the project, the angle of the PV array and all that stuff, and the orientation. But then if we analyze monthly, then we can understand in which month we are producing the most energy. In this case, July. But it's because of the amount of sun hours that we have in July. Because when it comes to the peak energy production, April is better than July. So these are the kind of things that we have to look at, and these are the kind of things that we have to, if we don't explain that to our clients, at least we need to know what we are doing. And based on our clients' needs, we have to make some decisions. We have to increase the production in January. Why? Maybe because in August or in June and July, and August, the building is not operating because there are holidays for everybody. So we are not concerned about this production. But if we are using the building in January and February, then we have to focus on those months. Okay, so I would like to have a straightforward answer to all these questions. What is the best month? What is the best orientation? Well, the best orientation is always south. That's the only straightforward answer that you can get. But what's the best angle? It depends. It depends on the latitude. It depends on what month you want to increase the production. So it takes time and it takes experience and it takes meetings with the client and with the electric companies, and to understand the ratio between the sell, when you sell energy or you can get energy from the grid. Okay, so it's not as simple as to say, okay, the tilt 45 degrees and how many panels? 10. No, you have to analyze it, analyze different parameters. Okay, so that's it. We have to master the PV watts. We have the yearly, the monthly production, and we have the daily and hourly production. And you have to be able to create graphics, either daily, monthly, weekly, or whatever. And then you have to be able to answer what is the peak. That would be another answer for a quiz. What is the peak energy production or daily production in April? Okay, so the peak energy production in April will be on, well, I don't know if this is April or in this month. So it would be this day. And what is the peak production on this day? So here you see that we can read the value. It's 110231. Okay, so this is the peak energy production. Just by hovering the mouse, we can get the value there. Okay, so let's. This is the quiz. I will prepare another quiz by this Wednesday. So again, I will explain something the first hour, and then the second hour you will have to complete this quiz. And we will do this next Wednesday or Wednesday, this coming Wednesday. And then next week we will prepare another quiz as a rehearsal for the final exam, and that's it. But now I want to show you what we did with Revit. So you remember that we had the TDS building. And on this final assignment, let's analyze what we have to do. Okay, so first we have to define the spaces and construction details. I have an example here. Okay, so this is about defining the spaces that we are analyzing. I told you to analyze at least 3 spaces. It can be the studio, the crit space, this one, and I don't know, it can be either the lobby or this classroom or the computer lab. At least you have to analyze 3. Then you have to go to construction details, and we have to use this Excel file. So with this construction detail, we have to figure out what we have here. So what is this? This is thick studs. Okay, so this is probably a gypsum wall. We know that building, and we know that the finish, the internal finish of this wall would be a gypsum wall. So we can work with this Excel file and this. So interior, we will have gypsum. The thermal conductivity of gypsum, it's gypsum board, it's 0.98. Okay, so here it's 0.98. What's that? What's the thickness? Apparently, this is thick gypsum wall board. GWB stands for gypsum wall board, firing on 2-inch studs secured to CMU. Okay, so here we have 2-inch stud. So this is the stud, and the stud is secured to the CMU, to the concrete masonry unit, and then we have the board, the gypsum board here. If this is 2 inches, how much can be? Maybe it's 3/4 or 1 inch. It's not relevant, but let's say 1 inch, it's fine. Okay. Then this is the stud, but what we have here is it's an air chamber, because this is the studs. We have studs every, let's say, 3 feet, but we have air there. So this barrier would be air. The width is 2 inches. And what is the thermal conductivity of air? Is 0.9. So this is 0.9. Then we have the concrete masonry unit. So the next is concrete masonry unit. Do we have information about the thickness of this concrete masonry unit? No, we don't, but I would say that is 10 inches. So let's say 10. And if we want to know the conductivity, the thermal conductivity, we have to go to concrete. Concrete. We don't have concrete masonry unit, but we can use this one, 4.1. It was 4.1. Okay. Then what is this? This looks like self-sheet waterproofing. Okay, so we have a waterproofing membrane here. Waterproofing. Membranes, it doesn't matter. The width is it's a membrane, so it's going to be something very thin. It can be in inches, 0.1. Okay, the thermal conductivity of waterproof. What are the elements that we can use as a waterproof? We can use either asphalt or mineral, stone. Yeah, something like that. So waterproof, it can be asphalt. We don't have the EPDM membrane. But it doesn't matter because it's very thin. So let's say that it's a 4.3. There will be an issue with the vapor resistivity. So with this one, we do have to be careful. So let's work with the default vapor resistivity. Let's type 0 so far. So we have the waterproof, then we have the rigid insulation. Rigid insulation. What is the thickness of this rigid insulation? We do have information here. We don't. Okay, so this detail can be better. So don't think that we have paid that because we have paid for it, it will be perfect. No, we don't have information about the kind of insulation and about maybe there's another drawing, but it should be here. If this is 10 inches and I know that the brick is 4, so this can be 6, yeah, kind of. So let's say that rigid insulation, it's 6 inches. And the thermal conductivity of this rigid insulation, when we are talking about rigid insulation, we are talking about polystyrene. Yeah, this one, it's 0.173. 0.173. Then there's another air chamber here. So this, if this was 2 inches, this can be 2 inches as well. Another air. The width is 2 inches. And the thermal conductivity is 0.9, it's the same as this one. And finally, we have the brick. So for that brick, the width is 4 inches. And the thermal conductivity of brick is this one, 3.47. Thermal conductivity, 3.47. And for this one, if we don't have any other layers, we can type 0, and that's fine. So the R value of this wall would be 44.73. It's quite good. I mean, it's almost a passive house, and we were, yeah, and this is what I was expecting from this wall. Okay, so here we have the graphic. This is the temperature. What about the dew point temperature, this orange line? Well, we haven't selected any vapor resistivity yet, so we can do it. First, gypsum. If we are working with gypsum, where is it? Gypsum. Here, the vapor resistivity can be around 60. So let's make it 60. The air, the vapor resistivity of air is very low, 5. Let's say 5. The CMU, the concrete, where it is? Concrete is 50. The waterproof layer, that's interesting. Waterproof, usually vapor resistivities are quite high. We don't have information. We have used asphalt. Okay, so it's around 100. Bitumen, it's another waterproof layer. Yeah, something between 100 and 200. Let's say 100. The rigid insulation is rigid. Oh, it's the polystyrene expanded, so it's 300. The air is 5 again, and then the brick is 50. Okay, if we are doing this and we look at the, okay, so we see that there's a risk of condensation here. So what can we do? If this happens, then we need to include another. I always recommend you have a waterproof layer outside. Well, this is inside the yeah. So this is inside the rigid insulation. That's good. Probably 100 is not enough. If we make this, let's say 500. Yeah, it's getting better. And if we make it 5,000, 50,000, something very high. Yep, we don't have any condensation risk here. Well, we have been talking a lot about air barriers and vapor barriers with Peter Yost and Mike Lacrosse last week. So by this time, I'm sure that if you think about it, it's a mess. So do you have any idea of what we have to use? Is it good using air barriers, vapor barriers, inside, outside? As a rule of thumb, I told you that in cold countries, in Kim, having something that it has a high vapor resistivity inside the thermal insulation, it always works well. On the other hand, there are people claiming that, okay, if you have this barrier here, you don't let the water vapor water vapor go out the building. And that's bad because there will be a high concentration of vapor here and it will end up condensating there. Yep, but you can solve this with a good mechanical ventilation system. Okay, so I think this is the right option that we have in this building. We have rigid insulation, we have something, it's not vapor, but it's waterproofing. So it has a high vapor resistivity. And then we can play with this because not all the barriers have the same vapor resistivity. We need to know what we need. Okay, so and we can deal with the provider. Okay, so I need something with vapor resistivity that is above 5,000 or whatever, and then they can supply you this kind of material. But it's not. Okay, so again, there is no straightforward answer to that question. Shall I use a vapor barrier inside or outside? Well, as a rule of thumb, I would say yes, use a vapor barrier inside the thermal insulation, as a rule of thumb. But then it depends on location, it depends on the use of the building, it depends on the rest of the layers of the building. Okay, so it's tough making these kind of decisions. But this is what you have to do. You have to copy this chart. If you can show me that you have solved the condensation risk, that would be great. Okay, so after analyzing this wall, you can copy this chart here, and this is the wall. So I don't know, you have to create a nice report. So if we're analyzing the wall here, you can have the wall detail. And then this graphic with all the materials here. Okay, so we need to do this at least for the wall and for the roof. So here you have a detail of the roof. You can use this. What is this? We have the gypsum board here, this false ceiling that we have in this class. Then we have the chamber, and this is not 2 inches because we have to hide the structures and the pipes. Okay, so in this case, we have the false ceiling, and probably there will be like a 2 feet or 2 foot air chamber here, probably. Then this is the deck, so that would be concrete, and that would be the rigid insulation. As you can see, the rigid insulation is thicker in the roof than it was in the wall. Okay, so this is the rigid insulation of the roof, and this is the wall rigid insulation. So if these were 6 inches, maybe this is 10 or 12. I don't know, it's up to you. But analyzing this detail, then you have to copy the dew point analysis of the roof, okay, with all the layers here and this graphic. Then this is something that most of you have already done, the analysis of this PV open rack here. You have to use different degrees, so anything from 10 to 20, it's fine. And then you have to compare this to this. And this option should be anything from 35 to 45 degrees. And then you have to compare these two options. And we can compare the total production. When we are comparing two kinds of PV arrays, it's not we don't need to look at the final number. Okay, so the final number here is 209,000 kilowatt hours per year, but this is the total square meter or area of this PV array. Here we have less energy production, but less PV panel area. Okay, so here I think there's something missing. The energy production is this, but here you have to insert the area. This is 958 square meters. So it's interesting. Calculate the production per area. So here we have 2,906 divided by 958. Okay, so this is 2. So that means that we have 218.89 kilowatt hours per square meter. Okay, and this is the important figure, not the total, but this ratio between energy and area. So we have to do the same here. Here the area is 286 square meter. And then what is the production? We have to calculate 66,582 divided by 286. And this is 232 kilowatt hours per square meter. Okay, so now we can compare both options. We have this one, this is 218, and this one is 232. So this is better. Okay, so in terms of production per area, this option shows better numbers than this. In terms of total production, this is much better because here we have 2,000 and 9,000, and here we only have 66,000. But in terms of performance itself, this is more efficient because with less area, we produce more energy. Okay, so now I told you last week that this is best. This is the best option because this is what they have decided. But now looking at this number, at the ratio between energy and area, I might change my mind. So maybe they did not select the best option. Or maybe they did. But now we have something, we have different arguments, and we can discuss different things. And if you think that the total number is the most important thing, go for this solution. If you think that this ratio is the best or the most important, okay, go for this option. And then we have the economic option. We haven't talked about this, but that would be the third factor that we need to analyze. We are not doing this because, well, there are a lot of things that we don't understand, like the return of investment, the discount rate, the interest rate. So there are things that we are not, they are not in our control. So that's why if you go for management or business, minor or major, you will get to understand these economic parameters, and you can apply those economic parameters to architecture, and that would be great. Okay, so these are the kind of conclusions, because you always ask me, what are the conclusions? I don't know, these kind of things. You can analyze the total production and then the ratio and compare it. So in terms of the total, this is the best, but in terms of the ratio, this is the best option. Okay, now we have the passive solar heat gains, and here, well, you remember that you have to do this in a space in which we have a large area of glazing. So this grid space, we have a lot, or you can analyze the lobby, I don't know. And if we analyze this yearly, but it's better if we analyze this in summer or winter. In winter, I think that's good because you can see that we have a lot of heat gains. In summer, it can be better. If we didn't have this green or yellow color here, I think that would be better. How can we solve that? I don't know, by extending this, by creating another overhang here. I don't know, we're not going to analyze this, but at least we need to understand that in winter, we have in this space, we have, and probably in this lobby, there will be a lot of solar heat gains, and that's good. Okay, so that's a good option in winter. In this kind of, can we improve the performance in summer? I think so. I think by changing the design, we could increase the performance in summer. Then we have to do this. Okay, so we have to work with PV watts, daily analysis in January and July. You have to do this open RAG analysis because this is Revit. Okay, all these analyses are made with Revit. And now here you have to start working or copying the PV watts analysis. So the first thing is the well, the first one would be the yearly analysis. So you have to, well, we have already done this. Okay. But this number should be okay. So this is 179, and this is 209. Well, something like that. So we have already done this, so that's why it's not included here. But now we have to download the hourly results from PV watts. And I think now we can analyze different things. So we can analyze the monthly performance. Okay, so we can analyze this in, let's try to make the most of the space. So we can copy like 4 months on the same slide. Okay, January, February, March, April. Okay, you can continue to do this. So you can prepare a monthly analysis, a daily but monthly analysis. Make sure that that scale is the same. It's pretty cool because if you just copy the Excel file, you can change here in PowerPoint. You can change the scale and all that stuff. Okay, so you don't have to go back to Excel and do it. You can just do it here. Okay, so now we are analyzing this from 0 to 140,000, and now we can see and make sure that all the graphics are the same size. Yeah, so that we can. We can also include a daily analysis in. Okay, so we can include daily analysis on the first day of each month. Okay, so that would be January 1st. We can do this every on the first day of each month. Okay, so on February the 1st, we can select here this, insert. So that would be February the 1st. Okay, so you can do this on the first day of each month. And well, we can have information about the peak. So the more the sun, the highest, or the highest is peak value, the daily peak value we will have here. Okay. So let's try to analyze this daily. Okay, so we have a lot of information. If we are using the PV watts and we have this Excel file, there are a lot of things we can do, and there are a lot of things we can analyze here. First, comparing different months, then even comparing different days, we can understand. And if we have the yearly performance, that's all we need. Okay. And finally, we have to work with this heating load analysis. Well, there are different ways we can do this. I showed you last week how to do this with Revit. And today I'm going to show you how to work with Insight. I don't know, a few years ago, I think it was easier. And everything that is easier is better. When things are getting more and more complicated, maybe if you're an expert, you have more options and you know what to do. But if we are beginners on this kind of building energy loads analysis, the more complicated, the less useful, because we are young architects, I'm including myself here, and we need to make quick decisions at the early stage of a design process. Okay, so I would like to have quite good information as soon as possible without a lot of effort. Then, yeah, when we are done with the design, we can go and we can analyze thoroughly what we want, the options, but the first design stage, I would like, okay, I have the model. So I have spent my time creating this 3D model. This is what I'm doing because, well, I'm an architect and someone has to model the building. So I have done it. But then, okay, so I want to make some decisions about the orientation, about the glass area. So I would like to have a quick response from the program. And we had this like 5 or in Revit 2016, we had this fast analysis, but now things are getting more complicated. Probably it's better for the last stage of the project, but for the early stage, and this is what we want now, it's getting more complicated in Revit. Okay, so I'm going to, first we have this, and this is quite easy because with this we can analyze. So I'll go over it again. So let's open level 2, and we're analyzing you remember that if we select the space, we change okay, we're analyzing the studio, and we're analyzing the grid space. Okay, so this is the grid space. And let's analyze the lobby. Okay, so this is the name here. The number is 200. No, I think I changed that name. Okay, so we're analyzing this classroom 203. So we're analyzing this space, the 3 spaces, 1, 2, and 3. But now we have to work with the space, and I think we did this before, but let's do it again. We can work with first so we have to go to the energy analysis tab here on the properties windows. Let's expand this. So we have to work with energy analysis. First, it's we have to click here because this is not a mechanical room or a locker room or a basement or an attic. No, it's something that people are living there. So we have to click here, this optical option. Then the condition type, it has to be heated and cooled. Okay, it's not unconditioned, it's not just naturally vented. So this has to be heated and cooled. The space type, now we have to select the building, what kind of building we are using. And it's a classroom. Okay, so it can be a classroom, why not? And here we have to select all these things, especially the important is the infiltration airflow per area. Oof, this is too much, but at least we can work with the schedule. Okay, so with the schedule here, we can work from 8 a.m. to 9 p.m. If we're selecting the building, by default, we have this from 8 a.m. to 9 p.m. I think this is good. This is enough. But you can change it here. If you want to start the classes at 7 a.m., so you can set that at 7 a.m. we have 50% of the classes working, and then you can change it. Okay. Then the lighting schedule is the same from 7 a.m. to 9 p.m. The power schedule from 7 a.m. to 9 p.m. But you can change it. I think if we select the right, we select a classroom, by default, we have values that go well. Then the outdoor air per person, we always fix this at 20 CFM per person. And then we can select the outdoor air per area. So there are 2 things. I don't know, I have memorized this number, the 20 CFM per person, so I prefer to use this. And so for the area, I don't know, we can type it 0. And then the outdoor air method, we can say the maximum by people or by area. So if we have selected 0 by area, the maximum is going to be by people, always. Okay, so let's select this. Or Yeah, maximum by people and by area. The heating set point is a 70, the cooling set point is a 74. That's interesting because, well, in winter, we set the comfort temperature slightly lower than in summer. Why? Because in winter, we wear more clothes on, usually. And in summer, we wear less clothes. Okay, so usually we tend to lower from 70 to 75, it's a comfort temperature, but the heating set point is closer to 70 and the cooling set point is closer to 75. Okay, so that makes sense. We have just to go over this. If we have selected the classroom type, most of these values by default would be okay, except the outdoor air per person. I don't know, I would use always 20 because I think this is the correct way to do it. Okay, so when we have this, then we have to check the create space. This is checked, it's heated and cooled. The building, is this a classroom? Yeah, I think this is a classroom. And now that we select this, everything is set. So this is 20 again, and we have the same schedule. Okay, so we have, once we have done this with this classroom lecture space type, then we have this again. And then for this classroom, heated, occupied. And now by default, you see that the outdoor air is 10, but if we select the classroom, now it's 20 because we have already changed it. Okay, so we are analyzing now three spaces. We are analyzing this one, the studio, the CREAT space, and 203 classroom. We have already changed this. It's occupable, heated and cooled, classroom, lecture, people. Okay, I didn't do that. What's the number of people? We can change it here. What's the number of people in this classroom? 20? Is it 20?
Yeah.
What's the number of people here? Depends. 30. And what's the maximum number of people here on that space? 50. Yeah, I think we changed that before, but it's up to you. Don't tell me that here there are only 2 people because I don't believe it. So everything that's between 30 and 50, that's fine. And yeah. So once we are done with this, we can go to at least work with the energy analysis. Okay, so we have to make sure that the spaces that we are analyzing are like this, and the use of the space is the right one, and at least the number of people. Here we have electrical loads. It's by space type. Since we have decided that this is a classroom, I think we can trust on these default values. But when it comes to the number of people and the CFM, yeah, we know those values, so we can change if the default values are not what we want. So now we have to analyze, create this heating and cooling loads analysis. And here, well, here we have here we can select the building service. I told you to select this one, split system with mechanical ventilation. This is what we have in this kind of classrooms. We have a split system with a mechanical ventilation system. Okay, report. The building infiltration class, make it tight. None means that we don't have any infiltration. This is not realistic. Loose is a bad building. Medium. Okay, so if we are working with a TDS building, we can assume that this is a tight infiltration building. So we can select this one. Now on details, These are the spaces that we are going to analyze, the grid space, the studio. Okay, so just check in the studio space, we have a classroom, lecture, training. This is what we have selected, 50 people. Okay, so just check the grid space is 30 people, classroom, lecture, training. So just check that, and this is the 203 classroom. It's 20 people. So let's check that we have changed there. It's the same thing that we have here. Okay, we can save settings and we can heating load, calculate. Okay, so we have the building summary, but I want to go to the space summary, and then we have to go to the studio. And well, I told you to copy all these. This is classroom 3. I know what I copied here, but you have to copy the studio space. And then by looking at this, well, there's a lot of window space in the studio. So we have a cooling and heating loads through windows. Yeah, so that makes sense. Then the next one is the roof. Okay, so usually the roof is the heating loads in the roof are higher than the cooling loads in the roof. That makes sense. Well, we have skylights here. Do we have skylights in the studio?
Yeah, we have 2 in the studio.
Yeah, the circular ones.
Yeah, the circular ones. Okay, so we can even include skylights here. We haven't done it, so that's why 0. But now we have infiltration. Okay, so you see that we have infiltration loads in cooling, and we have infiltration loads in heating. The heating infiltration loads are much higher than the cooling infiltration loads. That makes sense because the difference between comfort temperature and outdoor temperature in winter is higher than the difference between indoor and outdoor temperature in summer. Okay, so that's why infiltration loads are higher in winter. So everything makes sense here. And we have the peak cooling and the peak heating. So this is the first thing that we have to analyze, and then we can analyze through different components, make sure that the, well, even with a triple glazing, the window shows always the highest heating and cooling load. That's a fact. And here we can look at the infiltration and the infiltration loads. As you can see, for the cooling components, we have lighting, power, people. What does it mean? If you are working with a computer and if you, well, especially the desktop, if you touch where the ventilator is, you understand that this is ventilating the system. So it's generating, it's releasing heat to the room. Okay, so that's good in winter because we don't take that into account in winter, in heating, but in cooling, if we have a lot of devices on, we are generating an extra heat that we have to get rid of. Okay, so those are the internal gains. What are the internal gains? The lighting, the power, and the people. So people, just by being there, our temperature, our body temperature is around 96 Fahrenheit, I think. And the indoor temperature is 70 or 74. So we are releasing heat. Okay, so just by having people and power and lighting, we are releasing heat inside. So those are the internal heat gains. we have internal heat gains when it comes to calculating the cooling component. We don't have, or we don't consider heat gains or internal heat gains when we are calculating the heating component, because we are on the safe side. Okay, so this is something that makes us waste more or spend more energy, cooling energy, but we are not considering this when we are calculating the cooling, the peak cooling or heating. Okay, so those are the internal heat gains here only in cooling. So by looking at this, I can trust this report. Yeah, kind of. I trust this report. So you have to do this with the classroom, with the lobby, and the studio. Okay, we have to look at this. Since the studio is bigger, the peak cooling and heating loads should be bigger than the classroom. Well, it depends on the amount of glass that usually the bigger the space, the higher the peak loads. So here in the studio is 74 and 29. In the classroom is 32 and 17. Okay, so just looking at these figures, we can, I can rely on that information. Okay, and what's left? The inside analysis. When we are here, you know that by clicking here, optimize, by doing this, you are sending your data, your building to the cloud. And then it's performing cloud energy analysis. It takes time, and I mean, it takes hours. Okay, so I did this. I remember that I clicked here on Wednesday, and a couple of hours later, or 2 or 3 hours later, I received an email that the analysis was there. And it is there. Where? Well, this is the insight. I'm going to, okay, so if you can, if you want to open that analysis, you can type insight 360autodesk.com. Get started. And we have to sign in. Okay, so it's remember that you have to sign in with your KineState account, password. What is my password? Now I receive a digit code. Okay, so now I am in my Insight. Even this was easier in other versions. You can create a new one, or you can go over. So this is, I sent this on May the 10th. Yeah, today at 6:15 a.m. Yeah, I did that. Okay, so this is the last one that I sent. So I just click on this one. And this is the TDS building. We can, okay. So first we need to understand this. This is the, here we can adjust some settings. Okay, so click on settings. And we have Imperial. We can analyze this in terms of cost or energy use. we're not talking about money yet, but we are going to analyze the energy used. That's important. You want model widgets to sort by importance. Click yes here, because this is what we're going to do now. And then the dollars. Okay. So if you want to select those settings, you can select imperial, energy use, and sort widgets by importance. So once we are done with this, we can click on the analysis, and there you go. So this is the first element, or the first value that we have to analyze. So we are spending here 202 kBTUs per square feet per year. Okay, so this is quite important because when we are trying to meet the passive house standards, there is another. We have passive house standards when it comes to the R value of the walls, the R value of the roof, the windows, but there's always standard, there's always something about the total energy consumption per square feet and per year, because this is what the TDS building is going to consume more energy than a single family house because the building is bigger. So that's why we need to divide this by the area. The same thing we did with the PV array to understand which option was better. Okay, so this option of dividing energy dividing energy by area is what we have to do. And what is the passive house? Okay, look at this. Remember this number. It's 202. So what is the passive house? The passive house standard, we have this Passive House Institute of the United States, so we can rely on this source. And here, Building Science Corporation, what is a passive building? Okay, so the result was the North America. This is in 2015, they had the last meeting and they decided the standards in North America. So click on that link. And here we have a map of North America and Israel. Interesting. And also in Norway. Okay. Great. This is Hawaii. Oh, yeah. Okay, so let's stick to our nice place. Okay, so we are here. This is Laconia. I don't know where this is, but it has to be. This is Concord. So we're skiing. This is Springfield, Lebanon. Well, I don't know. You can select one of these because those are the weather stations or the places where we have data. Okay, so something around here. We are.
King had a little thing on it.
Where's King? Ah, King. Okay, great. Okay, so let's select this one in King. So a passive house standard, this is zone 5. Okay, I remember that when Mike was talking to us last week, he mentioned the zone 5, 4, 6, whatever. King is 5, and then if we go north, it's 6. Okay, so there is something even worse than King, which is something that it's close to Canada, in Maine, or okay, that 5. 1 is the mildest zone. 6, I think, is the toughest in terms of weather. So King is in the 5, and this is the heating demand. It's 6.5 the heating, 1.6 the cooling. This is kBTUs per square feet per year. This ICFA, it's indoor conditioned floor area. Yeah, indoor conditioned floor area. Okay, so this is the floor area of floor area of the building. Okay. So look at this. The heating demand. This is the requirements. So we have to lower the heating demand below 6.5 kBTUs per square feet per year. The cooling demand has to be below 1.6. The peak heating load should be below 5 per square feet, always per square feet. And then the peak cooling load. Okay, so this is just the heating and cooling loads. Are we meeting those requirements? Let's analyze this, the loads report. So in our studio space, the peak heating is 29,000. What is the floor area? We have here the floor area. Well, it's the same as the roof area, 5,000. Okay. So what is our performance? Let's open the calculator. So the performance is.
Fernando, I don't know if it's just the projector or.
No, it's my screen.
Okay. Out.
You have to. Okay. So this is 29,450. 29,450 divided by the floor area of that space. We are working with this space, and the floor area of the roof area is 5,139. Okay, so this is 5.73. This is kBTUs per square feet. If we go to the passive house, it should be 3.9. Why? It's because of the large glass area that we have in this building. Okay, so if we reduce the glass area, probably we could meet the passive house standards. We are not meeting the passive house standards because it's extremely restrictive when it comes to windows. Okay, but this is a reference. Are we close to a passive house standard? Well, here we have the information. We'll have to go space by space. It's easier going space by space than the whole building itself. Well, here we have the peak. This is the peak heating. What about the peak cooling? I think for the peak cooling we are worse because the peak cooling is 74,000. It's 74,545 divided by the roof area with roof area 5,139. Okay, so this is 14.5. According to the requirements, the cooling, this is the cooling load, it should be 3.9. Okay, so we are good for the heating because the heating is 5 and we are in 5 point something. But when it comes to the cooling, this is not good because the maximum cooling load should be 3.9 and ours is 14.5. Okay, so we are far from meeting the cooling passive house standards. Okay, so even this building, which is a LEED Platinum building, we are far from these passive house standards. And we are far from passive house standards because the amount of glass that we have in the building, I wouldn't change it. I mean, but we have to understand where we are, and meeting passive house standards, it's quite tough. So that's why I don't like this. They should give you some freedom because there are things that are not measured in terms of BTUs, or there's something that make people happy. And this is something that you cannot measure with these just energetic parameters. Okay? Anyway, if we look at the inside, this figure 202 is the total energy consumption, not only the heating, not only the cooling, but the energy, the computers, so everything that is using energy, we add everything up, and this is the final figure. And not only heating and cooling. For these passive house standards, we have information only about the heating and cooling. But then we have, and that depends on what kind of building we are using. In a single family house, we don't have 20 computers in one room. In a school, we do have this. Okay, so that way this number is not enough to understand if we are good or not. Okay, we run out of time. So on Wednesday, I will continue to explain this, and we will go over all these options, because all these are options to improve the energy performance of the building.